Thanks a lot for joining us today. We wanted to talk a little bit about privacy on the IC and to introduce the topic. It's one of those things that with blockchains, we don't really talk about very often. And I think when it comes to data privacy, generally in the digital world, we were doing okay, maybe 10 years ago, and but it took quite some while to get going. But we got going, and then blockchains came along and decentralized everything, and then we were back to zero in terms of data privacy. So now the crypto is there. I mean, not just we, but generally the crypto world made quite some improvements in data privacy and things that they can use. So it's now a matter of actually sitting down and using them and actually thinking, how can I use the tools that we've built in such a way that we can add like really nice privacy and really nice use cases and build super cool things to get back to that point of privacy that we had maybe 10 years ago when the internet became encrypted and when Signal came and gave end-to-end encrypted messages and things like that. So this is basically where we want to get. And Greg and the team here had some very nice ideas about how we can achieve this. And so, yeah, today is the day that we start talking about that. Just for a little bit of context, we called this so far threshold key derivation. We call it sometimes VET-KD. Sometimes now we call it on-chain encryption. There's the term chain key encryption floating around as well. And we are trying to think of a name that is basically suitable, that's somehow understandable, that people will kind of not question or raise an eyebrow. So if you have questions or if you have suggestions, we're happy to hear what we should call this feature. This is the first community conversation where we'll just kind of introduce the vague ideas. We want to kind of develop these ideas with you. So if you have use cases or if you have questions or if there's a problem that you couldn't solve before, let us know and work together with us so that we can kind of design this together a bit more openly maybe than previous things were done. We're very much, curious to hear what you want. So yeah, this will be the first kind of more introductory community conversation, and then hopefully we get some nice feedback from you. We pull it all together, propose a design, and then we'll have a second community conversation to update you on that. Ask questions, give comments, give suggestions, type them in the chat. I'll ask Greg, I'll bug him on your behalf, or ask in the forum or Twitter, or send us smoke signals. I don't care. Ask questions however way you can. It would be great. Join the conversation, tell everybody why you want this. It's a very cool feature, and there's like a ton of stuff that we can do. And we have some nice plans for next year to engage the community as well in this respect. So yeah, the more you get involved, the earlier, the better. And yeah, I guess I hand it over to Greg a bit to give you a bit of an overview of his suggestions of how we can get some privacy on the IC.
Cool. Thanks a lot, Aisling. Yeah, happy to take it away. Good. Yeah. So welcome from my side as well to this community conversation. As Aisling said, any naming suggestions very welcome. So threshold key derivation, on-chain encryption. I suggest that we just dive into it to see what it actually does, and then you can come up with your creative names. So we're going with the running name of on-chain encryption for now. What it actually does, it would be a feature that enables canisters to deterministically derive strong cryptographic keys. Now, why deterministically? We have a random tape that you could use to generate random keys in case you need one. It's just that like once the random tape is gone, then you don't have it there. We want this to be something you can derive a strong key, and you can rederive it later if you need it again later. So this is what this feature is going to do. What those keys can do. Those keys you can use for symmetric encryption, for asymmetric encryption, for signatures, for a whole bunch of things, actually. We'll come to that in a minute, what the use cases are. Now, the big thing about this is that the keys that a canister derives can either be delivered straight into the canister, which has some use cases, so that the canister and all the nodes in the subnet learn the key. But this is the big thing. They can actually also be delivered straight to the user front end, so that only the encrypted key is visible to the nodes, not the key itself, and so the key itself remains hidden from the nodes. And that's what gives us the main use cases of this feature to achieve privacy on the internet computer. Things that we can do with it is having canisters store confidential data, providing end-to-end encrypted storage, end-to-end encrypted messaging, even social networks, and also conditional decryption, things like time lock encryption, deadman switches, MEV protection, which is minor extracted value. We'll come to that at the end of this talk. So there's a bunch of features that you can do with this one interface that we would build. Now, why do we want to do this? Ash already sketched the context for this. So blockchains in general have been good for security if you're talking about integrity and availability of dapps, of data. But they've actually been bad for confidentiality because of that blockchain being either public or at least being public to all of the nodes that are producing the blockchain, as is the case for the internet computer. Every node has to keep a full copy of the state. So if before in a centralized model, there would be you're trusting one company to keep your data secure, now you have to trust every single node on the network to keep your data secure. So for confidentiality, replication is actually a bad thing. Now, the other thing is managing user-side encryption keys is actually pretty complicated. You could do encryption on the blockchain already today, but you would have to require your users to keep their own keys. Problem is where to keep those keys. In browser storage is not great because when a user deletes the cookies of a browser, also browser storage gets deleted, and it's kind of exposed because it gets written to disk where it can become victim to malware on the user's devices. So it's not great there. Also, we don't have the support for trusted hardware that we have for authentication, and the syncing across devices is definitely difficult because something that is encrypted to one device will not be automatically decryptable to another device. So what we'd like to do with this feature is essentially open up the internet computer for a whole spectrum of business dapps, business canisters that require some form of confidentiality because there's personal data, because there's documents that are confidential being stored. Currently, it's hard to do that on the internet computer because all of the state is copied over all of the nodes. With this feature, you can actually give proper protection for that kind of data. And of course, a secondary goal is also that there's applications that previously would only be possible with a trusted third party or with secure hardware like time lock encryption or deadman switches. Now you can actually build them on a decentralized assumption on the internet computer. How we're planning to do so? The technical word for it is verifiably encrypted threshold key derivation, or VETKD. We'll come back to a bit more details in a minute. The main idea is that there's one master key on a subnet, that the secret key of that is secret shared across the nodes, and we give canisters access to a key derivation interface. Now, what is this key derivation interface? The main thing to think of is every string becomes a strong cryptographic key. The system API is sketched there, so any canister can call this derive an encrypted key and pass in some information, including the derivation ID, that is a string that I'm talking about, and turn it into an encrypted key. We'll come back to the API in more detail in a minute. So what we'd like to discuss in this talk is we'll first go over the mental model of this feature, how to think about it, how you can use this. Then we'll briefly mention the cryptographic foundations. We don't want to go all too deep into that, so we go faster because we want to talk about use cases. 3 use cases that I've prepared slides for are secure storage, end-to-end encrypted messaging, and front-running prevention, or this minor extracted value use case. So let's start with the first part, the mental model for this. So as I mentioned, the best way to think of this is every string can be converted into a strong cryptographic key. In a simple version of the interface, the canister can make a system call for deriving a key for a certain master key ID. We're modeling the possibilities there would be multiple master keys living on one subnet or on different subnets. But importantly, you give with that system call the derivation identity. So some sort of string that you want to turn into a strong cryptographic key. The master secret is threshold shared over the nodes, and the subnet does some operation on it so that this derived key actually becomes a strong cryptographic key derived from that derivation identity. If you derive the same identity twice, you'll end up with the exact same derived key, but no single node by himself could predict the derived key before it was actually computed. Now, you can kind of see this as the subnet is doing something magical with that string. It's like a fairy who is sprinkling the derivation ID with some fairy dust and strengthens that derivation ID into actually a strong cryptographic key that then you can use for other purposes. Now, what could then the canister do with that derived key? Well, what it could do, of course, is take a plain text and encrypt that plain text, symmetric encryption as a ciphertext, and store that ciphertext, and later when it needs to re-decrypt that ciphertext, then just derive the same key again and decrypt the ciphertext. Now, that kind of works, but it's not great in terms of security. What you would get is that this ciphertext, when at rest, what gets written to disk, it's actually encrypted, but a somewhat decent adversary who actually has access to a node and can look into its memory, not just its disk, the key is being used in the computation, so it would leak. So some security, but not great security if you use it this way. A better way to use it is if you would look at this derived key as an asymmetric cryptographic key. And what you would actually be able to do is that any users outside could actually use an asymmetric sort of encryption, identity-based encryption. We'll mention it more in a moment. But that allows you to encrypt a plain text to just the master key and the derivation identity. So just a string of the derivation identity, what can be public. Anyone can encrypt a ciphertext, send it to the canister, and when the canister decides that it's time to decrypt the ciphertext, it can call the key derivation interface, obtain the derived key, and then use asymmetrical decryption of that ciphertext in order to recover the plain text. Time lock encryption is a particular example of this. You could, for example, attach a condition that the ciphertext could only be decrypted at a certain point in time, and the canister will take care that the ciphertext gets stored and only gets decrypted when that time actually comes. Another thing that, so that actually already makes it more useful. Another thing that makes it very useful, especially for end-to-end encryption purposes, is that we have this extra feature of having the user front end generating a transport key pair consisting of a public key and a secret key. And the canister can then call its key derivation interface specifying the public key of that transport key pair, so that actually the key is derived not only in the clear, but is derived in encrypted form. And so the only thing that the nodes on the subnet see and the canister sees is an encrypted key. This encrypted key could be seen as like extra fairy dust being sprinkled on that derivation ID, because now it's like the transport public key and the derivation ID together that get mangled into an encrypted strong cryptographic key. The canister can then send that encrypted key back to the user front end. Because the user front end actually generated that transport key, can actually decrypt the derived key from the encrypted key, and then use the derived key for anything that it wants to do. For example, encrypting a certain plain text and decrypting the ciphertext at a later point in time. Right, so that's how to think about the interface. If you want to have more cryptographic details, what is actually behind this is a primitive called identity-based encryption. Identity-based encryption, like we cryptographers always like the Alice-Bob story where Alice is encrypting a message to Bob. What it allows Bob to do is to obtain a decryption key for his identity Bob from a centralized authority. And based on that, Alice can send her message to Bob using just Bob's identity and the master public key of the authority. Now, you would probably want to do this in a way where somebody can verify that Bob is actually who he claims to be. And you could imagine a scenario where there's like an inspector sitting in the middle who checks that Bob is actually Bob, and there's a transport key being generated by Bob, where the inspector then tells the authority, hey, you may want to encrypt that decryption key under Bob's transport public key. This is just to get the analogy straight to our encrypted decryption key setting. Now, what we want to do, of course, as we are allergic to anything centralized, is decentralize that centralized authority on the right and let that role be played by the nodes in a subnet in a decentralized way. And let essentially the determining of which identity is allowed to decrypt what or obtain what kind of keys, let that role being fulfilled by a canister. I'm not going to go too much into details right here, but the basic idea is that the derived keys that we're talking about all the time are actually BLS signatures. And what we're doing is essentially generating a threshold BLS signature on the subnet. So the master key is a BLS signature key, secret shared over the nodes. And if you enter a certain derivation identity, the derivation identity will be threshold signed. And the resulting signature will act as a key. It can be used as a symmetric key, but it's actually also the decryption key for the Bonnet-Franklin identity-based encryption scheme, which gives you the asymmetric use cases. Now, on top of that, we have to be able to deliver those keys, those BLS signatures, in an encrypted way to the user front end. And to do that, what we're going to do is algomal encrypt this BLS key, so that with the slight homomorphism that algomal still allows, we can actually verify encrypted key shares, and we can compress them into a compact encrypted key without having to decrypt them, and in an efficient way send them over to the other side. I don't think this is a talk to go into the cryptographic details, but for those who like to see the crypto equations, they're right there. You can look at it afterwards in YouTube. So let's go to the more interesting part, the use cases. So as I mentioned, some of the important use cases are in end-to-end encryption. One simple example would be an encrypted file storage application. We already have an application of encrypted nodes that currently relies on keeping the user keys in the browser storage with the disadvantages that I just mentioned. With this feature of threshold key derivation or on-chain encryption, what the user front end could do is first generate this transport key pair, the TPK-TSK on the left, and then send an ingress message to a storage canister saying, okay, could you get my main decryption key? So what the storage canister would then do is ask for a key derivation encrypted under the transfer public key that the user just sent, and for the user's identity. I'm here using the principal of the user. So this would be a principal for a user called Alice, and that's why the principal starts with something that looks like Alice. Anyway, this is just the principal. It can be any string, so you can actually use the principal as the derivation ID there, and get an encrypted key back. Now, when that encrypted key hits the canister can pass it on to the user front end, so that the user can then decrypt the key from the encrypted key, and with that key encrypt its documents into an encrypted document, and then in the next flow send, that is number 7 here, in the next flow store the encrypted document on the storage canister. So this is how you can drop encrypted files on a storage canister. If you want to recover your files, then the same user the same user Alice can regenerate a fresh transport public key pair. It doesn't have to be the same as the first one. Send a signed ingress message under her principal saying, okay, I would like to have this file name recovered, and by the way, this is my transport key that you should be using. The storage canister will rederive an encrypted key for Alice as in the derivation identity Alice's principal. Get the encrypted key, send it back together with the encrypted file to the user, so that Alice can recover the key and decrypt the file and recover her plain text documents. So this is how you could do this, to have a sort of like online drive kind of functionality with encrypted files that only the users themselves can decrypt, and not the canisters who are hosting the files. Another use case would be end-to-end encrypted messaging. Think of an application like, for example, OpenChat. This is just one way of doing it, but let me sketch how it would work. Again, so suppose that there are two users, Alice and Bob, who want to talk to each other. Then the front end of Alice would first generate a transport key pair, and then say like, okay, I would like to get the key to talk to Bob. This B0, BCZ, this is Bob's principal. So this is Alice's principal asking, hey, I would like to get the key to talk to Bob. The canister could then, for example, say, okay, so every pair of people, in order to talk to each other, they will encrypt their messages with the key that is recovered from using the derivation identity, that is the concatenation of both of their principals in a particular order. So let's say alphabetic order. So the chat canister will do exactly that. What comes out is the derived key, not in plaintext form, but in encrypted form. But that encrypted form can get decrypted by Alice. So she can actually recover this conversation key and then encrypt her messages to Bob under that key and send those messages off to the chat canister so that the stored messages can be stored in, the encrypted messages can be stored in the chat canister. If Bob then later on wants to say like, okay, I want to see which messages have arrived for me, then he would generate his own transport key pair and send a signed ingress message saying like, here's my transport key, tell me what's new. The chat canister would see like, oh, there's this message from Alice, so let me help Bob recreating that encryption key for the Alice-Bob conversation. And the canister would send the encrypted key resulting from that, together with the encrypted message, back to Bob, who can then recover the encryption key and decrypt the message and get the message out of it. That is one way of doing end-to-end encrypted messaging with symmetric encryption. You could actually make it slightly more efficient if you use the asymmetric use case. Because what Alice could do instead of deriving a key is asymmetrically encrypting the message to Bob's principal and straight away send that encrypted message to the chat canister. So this is where we use this identity-based encryption, the Bonnet-Franklin scheme. The great thing is that here, Alice can send her encrypted message without having to first get in touch with the canister to obtain a derived key. This is Alice can do this just in one flow instead of in three flows. And Bob, what he would do is pretty similar. He would ask for like, hey, is there anything new? The subnet would help him derive the decryption key that is now for his identity, not for the pair of identities anymore, and send all encrypted messages under that identity so that Bob on his side can recover the decryption key and use this asymmetrical decryption algorithm in order to recover the plaintext messages. So that was encrypted, end-to-end encrypted messaging. Of course, end-to-end encrypted email is exactly the same thing, just slightly less interactive. You can actually take it even one step further. You can start looking at end-to-end encrypted social networks where every post, every individual post gets encrypted using a key that is derived uniquely for this post. So you can assign a unique ID to every post that a person makes on the network and let that person derive a key for it, encrypt it to that user, so that the encrypted post is stored in the canister. And it's then up to the canister to enforce any access policy that the user chose for this post, so that only the users that are actually allowed according to the policy will be able to derive the key for decrypting that post and therefore see the plaintext content of that post. And all the while, the contents of the post remain hidden from all of the subnet nodes. So this is really an end-to-end encrypted social network that is actually hard to achieve in another way if you have a centralized entity where you probably wouldn't trust if some big social network provider would be sitting on and the encrypted post and the keys to decrypt all the posts. This way, because of the threshold assumption, you actually get that kind of security. Now, another pretty cool use case, we think, is where you want to prevent front running. In the previous use cases, it was always the user who was getting the derived keys and using it to hide information from the canister. This will be one example where actually it's a canister who will obtain the decryption key at some point, but only at a point in time where it's actually time to do so. This example here is one of a financial exchange, a DEX, where transactions are being submitted, but there could be a problem of so-called minor extracted value, which is a sort of front running, where in case a node would see a big transaction coming in, front runs that transaction and puts his own transaction in the middle to take advantage of the price difference caused by that big transaction. This is actually a big thing. You may know that on Ethereum, this is a really big thing. In total, around $680 million already got lost to MEV since 2020, and we're still counting. So this is one big problem in DEXs. Once you have a blockchain that has this on-chain encryption enabled, what users could do is use this asymmetric encryption in order to encrypt their transactions to a derivation identity that is an identifier of a time slot, say a slot of 30 seconds, 1 minute, 5 minutes, whatever the granularity is that you want to go for. And so this is one user, Alice, submitting her encrypted transaction. The canister will then memorize that transaction as being sent for that particular time slot. And all of the users actually start doing that. They all send encrypted transactions aimed for a particular time slot. The DEX sorts the transactions in the order that they come in, and so especially commits to the order in which they will be executed while the transactions are still encrypted. Only when that time slot has passed and no more valid transactions for this time slot will be accepted, only then will the digital exchange canister will actually call the system interface to derive the decryption key for this time slot. Only one decryption key is needed, and with that key can actually decrypt all of the transactions that were sequenced for this time slot and execute all of them in the order that they appeared in the canister before. So there's no more chance of doing any squeezing in between of new transactions at this point, because the order already got fixed before the decryption happened. Now, there are some similar use cases that you could use this for. Secret bid auctions, time lock encryption is something similar you can do. Deadman switch is something cool as well, which could be useful for journalists or whistleblowers, where a sender could encrypt a message, for example, some compromising documents, to a unique identifier associated with a document, send the encrypted document and the identifier to the canister. And the canister at that point would start a countdown timer that gets reset every time the sender gives a ping to the canister, a signed ping of like, yep, I'm still good, please reset the counter. If at some point the sender gets incapacitated for whatever reason, the timer will go off and the canister will be programmed to derive the key corresponding to the unique ID and decrypt the message and publish. So this is kind of like a life insurance, if you want. In case something happens to me, this information will be out in the open. There's other use cases that unfortunately we don't have time to go into right now. You can actually use these keys as BLS signatures by themselves. We already have that with certified variables, but this gives you a different way of using that. There are variations that you can use blind signatures with this interface. Unfortunately, don't have time to go into details as well either here, but you could do untraceable transactions in a Chaumian eCash style. And another thing is that we can turn internet identity to be truly private, not relying on this one secret seed that is stored in the state of every node in the II subnet. So we can make a better internet identity out of it as well. Anyway, this is what we prepared for today. Very interested to hear your questions, your use cases, and also if you have any suggestions for the feature name, please let it come. Thanks a lot.
I think I'm the only one that can make any noise, but I clap on behalf of everybody.
Much appreciated anyway.
Very cool. And I think there's a lot of questions, and maybe some of them were answered throughout, but there are a few kind of common themes that maybe I can throw back at you. One of them is around the throughput and the scalability of this type of thing. Is it going to be like threshold ECDSA, or is this a different game altogether?
Yeah, that's a very good question, actually. The cryptographic operations that you need to do for threshold BLS are much simpler than for threshold ECDSA because it's algebraically just much more elegant. And we've been doing some back of the envelope calculations so far based on the benchmarks that we have for basic crypto operations. And we are getting to, like on a 13-node app subnet, to hundreds to even 1,000 key derivations per second that a subnet could pull off. If you really want to like go full throttle on just key derivation. So this is like a couple of orders magnitude better than for threshold ECDSA, which, I mean, we don't want to brag about it. ECDSA is just way more complicated to do this, but so this would be considerably more efficient.
And I think one of the things that I think is important is that to stress is that these decisions are not made yet, like exactly how the scheme is designed or whatever. So when we say things like, you know, hundreds to 1,000, I mean, this can be decided, and you can help decide these things by telling us like what you need and how much power is on either side of either the device side or on that, you know, I mean, there are different kind of ways that you can tweak these schemes. So let us know. Okay, let's decide on a billion.
No, that's definitely true, because we're looking at different schemes, not just the one that I showed on the slide here, and different schemes have different throughputs. So like some of them are definitely slower than those hundreds up to 1,000. So and also bigger subnets, of course, will be more expensive, or higher thresholds, if you want to use those, will also be more expensive.
Another interesting question that Jordan is like on fire with questions, and they're great ones.
Nice. Glad to see that.
One of them that I found interesting is something that we didn't mention yet between us even, is about group chat. So you talk about end-to-end encrypted messaging. What about group chat? So between more than just the one-on-one conversation, but between 1 and 100 or so.
Yeah, very good question. Let me go back to, yes, end-to-end encrypted messages. Yes, so here you can see that for a conversation between two people, the canister chose to have as the derivation identity for the key that will be used to encrypt that conversation to be the pair of the two principals. You can use any identifier for this pair of communicating parties. In a group chat, what you just should use is an identifier for the group here, and it will be the canister who enforces that only members of the group will be allowed to obtain the decryption key for that group. So that will give you the flexibility that you want with people joining and leaving the group. Getting it completely right, you would, of course, have to be careful with people leaving the group who should not have access anymore. So you probably have to switch to a different derived key. So like the identifier of the group and something like a sequence number or something like that. There is space for design here. So doing this in a very secure way is delicate. Look at the Signal protocol. It's usually group chats that are the difficult not to crack, but definitely possible. And this feature would definitely help a great deal with it. But so essentially, all of it is possible by just choosing your derivation identities in a clever way that gives you exactly the right access to the conversations.
Yeah. And so stretching this a bit further is how you get to encrypted social networks and things like that.
Exactly. In the end, you could encrypt every message separately and then let the canister decide who gets access to this particular message. Yeah.
So Jordan again is saying this could enable a private chat app like never before possible. And like, I think we should also state, I mean, Greg's like, well, yes, maybe. But like, I think we should stress that, I mean, end-to-end encrypted email is not super possible. Like, it's not really used now. Like encryption solutions, privacy solutions suck, even in like a centralized setting. And so when we started talking about this was one of the most exciting points, is that actually, even in this decentralized, okay, you think like in the decentralized setting, everything is actually harder, but here, actually, maybe finally we can get end-to-end encrypted email. Maybe we can actually get group chat because, yeah, you have this kind of no central point of trust amongst the system. And then if you manage to encrypt everything on that, you have this kind of extra layer. So
yeah. Maybe one remark to add to that is that The protection that you get is, of course, only under the threshold assumption. If more than a threshold number of the nodes get corrupted and their master key shares are get put together, that adversary can decrypt all of the messages encrypted under it. If you want to protect against like the world being against you, then you probably have to strengthen this type of encryption with some actual user-side keys that the user then has to manage. So it's kind of like a balance that you have to strike between, okay, what assumption of the threshold am I fine living with? Because if you're fine living with that assumption, you can actually greatly improve the convenience of having keys because users don't have to sit on their keys anymore. They're stored server side, but in a threshold way. If you have like high security purposes, you may want to give those users the option to add another layer of encryption on top that is with a key that only they keep track of. At least you have the option in that case.
Speaking of keys and options, one of the first questions was about where are the keys stored and will every subnet have its own set of master keys or will there be a dedicated vetkd subnet? That you have to make cross canister calls to, or how will the setup be?
Yeah, that is a very good question as well, and actually still part of if we do the design process on this is like within the design scope of deciding that. Personally, I would be in favor of keeping things flexible so that we can decide which subnet gets to host which key. I would hope that this feature gets used a lot, so then we probably don't want to have like one subnet that has to process all of the keys. So we may want to have multiple of those keys, master keys, living around on the internet computer. Of course, we also need a backup solution because if that key ever gets lost, then everything encrypted under it is lost forever. So we may want to have a mechanism just like for threshold DCSA where one subnet can keep the backup of a key hosted on another subnet. There's things in the design space here that we can start looking at, and yeah, everything is possible. It's just a matter of making the design choices.
Yeah, cool. And I think, yeah, for me, it's pretty exciting that it's still quite open and that there's still space for discussion. So I really encourage people to join in, and especially like now seeing this chat, people have like good questions and a good intuition for what these things are. So if there's something that you don't understand or you want us to go into more detail about our tutorials or whatever, like with Dominic Werner, we thought about doing some developer workshops for crypto stuff so that we can kind of make sure everybody understands what they're doing with this next year. But yeah, always talk in the forum, ask questions. The thread is there. I will put the link in a second. But yeah, also, if you have any names, like people often talk about that we make decisions on behalf of the community. And yeah, here's one of those things where it's like, okay, now we're asking you, like, don't come back to us in 6 months later and say that, why are you calling it this? Why are the keys this way? Why is everything that way? Now is the time to actually have this discussion. So yeah.
We've been going back and forth a couple of times with the name here. It's
yeah,
like I think cryptographically the right name would be verifiably encrypted threshold key derivation, vetkd, which I like as a cryptographer, but I imagine to anyone who is not a cryptographer is just like, wait, what? Like it doesn't catch your eye as being something that could do cool stuff for you. So then the other directions to go to, like the main applications of it, which would be end-to-end encryption, privacy, threshold privacy, something like that. So yeah.
One of the nice things that came out in the chat actually was there was some questions about whether the boundary nodes are a weak point if they can see the keys. And so it kind of transpired that we discovered in the chat why we need the verifiability and why we actually need the keys to be encrypted as well.
Great research going on. Yeah, but indeed, so just to make clear, the boundary nodes will not see the keys themselves. They will see the encrypted keys, which are encrypted under the transport public key of the user. And I mean, they could stop messages from going through as a boundary nodes always can, but they cannot look inside the key and look inside the content. Yeah,
and they're verifiable then, so you can check that.
Yeah, the verifiability is mainly important for, well, of course, for the user to be able to check that he recovered the correct decryption key, but also for when the response to a derivation query gets included in a block and the nodes have to validate, notarize, and finalize this block. They have to be able to check, is this actually the correct response to the query? And this is where the verifiability also comes in.
Cool. So I'm very conscious that some neurons are going to be voting on some important stuff. And so there's one last question from Jordan that maybe, Greg, you can give a one-word answer to. Just wondering if Dfinity is working on homomorphic encryption in any capacity.
It's on our minds. Let's put it that way. This is not homomorphic encryption, just to be clear. So canisters here become routers of ciphertexts, but cannot perform useful operations on those ciphertexts. For that, you would need fully homomorphic encryption. In that sense, this is like, it's an easy step to take to make a big difference in terms of privacy, but it's not yet where maybe ideally you would want it to go. One way of doing that is through trusted hardware, things like AMD SEV SMP, which is actually something that we're also looking at right now. Unfortunately, these trusted hardware solutions tend to be not very secure because there's always side channel attacks on those. Google the one glitch rule to rule them all attack on the SMD SEV. So I prefer to keep that for use cases where we really don't know how to do it otherwise. But yeah, otherwise fully homomorphic encryption would be the way to go. I think we're quite loaded already with the features on our current roadmap, but yeah, like it's in the back of our minds.
As always.
As always.
Cool. Then I guess we wrap it up. I put the link to the forum in the chat, so I think most of the people here I've seen already interacting on the forum. So I guess you know it's there. The video will be on YouTube soon, so watch it back if we talked very quickly. But yeah, otherwise we look forward to the questions, continuing the discussion in the forum, everything on Twitter, also in Discover, everywhere. So yeah. Thanks very much. And I guess we leave it there and we go watch how SNS1 goes. Looking forward to it. Thanks
everyone.